All right, this is going to be the second part of the geometry Unit 6 Lesson 1 video. And so what I'm going to do here is I'm going to go ahead and work through some of the problems in the lesson because they're a little bit challenging. In particular, I want to focus on the proofs. And basically what I'm going to commit to you is that because I think we'll probably have varying ability levels when it comes to doing proofs, I am going to complete proofs on the video lessons with you. So at least you can see them completed correctly and have a general understanding of how they work. So what a proof is in geometry, and this would have been something you covered in the first half of the class, it's a way of systematically using definitions, theorems that we learn, systematically prove something based on some other piece of information. So I'm going to read through this one and then we'll go through it. So it says given, and this means given means this is what we know. We know that there is a parallelogram EFGH right here. So that's what we know, EFGH. And they want us to prove something that we learned in this lesson, which is that EF and GH are congruent and GF and EH are congruent. So they want us to prove something. Now, we learned that in this lesson. We talked about that in the first lesson video. But then the question is, how do we know that? How can we prove that using what we already know in geometry? So we're going to walk through this. So the way a proof works is you have a statement on one side, and then you have your reason on the other side. What is the theorem or definition or property that we're using to prove that? So let's talk about this one. The first statement is always the given. EFGH is the parallelogram. That's given. That was given to us at the very beginning. So then we look at the next statement. The next statement says that EF is parallel to GH. That's what this says. And EH is parallel to GF. Well, that's the definition of something. So let's look at this. It says, and we have a few options. There's only a few that make sense. Actually, there's only one that makes sense. There is no definition of 4, definition of 3, definition of SAS, but there is such a thing as a definition of a parallelogram. And actually, that is exactly what's going on here. We know that the definition of a parallelogram is that it has opposite sides that are parallel. So that's why the parallelogram is the word that goes in the blank there. Okay, so we learned that. So now we know there's parallel lines here and here. So we go to number 3. It says angle 1 is congruent to some other angle, and angle 2 is congruent to some other angle. So it's like, what angles are they congruent to? So we look up at our diagram, we see angle 1 and angle 2 are down here, angle 3 and angle 4 up here. So it either has to be, just common sense says, either angle 1 is congruent to 3 or angle 1 is congruent to 4. So we have to decide which one we think it is. So we do know, however, right here, that the reason that we're saying what we're saying in number 3 is due to the alternate interior angles theorem. So the alternate interior angles theorem was a theorem that you learned in back in the early stages of geometry. And it said that when you have two parallel lines and a line going through them, then there are congruent angles here, and there are congruent angles here. And if I could cut this out and put it over here, you would see that actually angle 1 and angle 4 are alternate interior angles, and angle 2 and angle 3 are alternate interior angles. Let me erase all of this. So what we're saying is we know now that these 1 and 4, and then of course 2 and 3 are going to be congruent. So we've proven that. Let's erase this. All right. Oops. So then what is next? Now it says EG is congruent to EG. Like, well, that's obvious. Well, this is a special kind of property. You'll see this happen a lot in proofs, and it is called the reflexive property of congruence. Reflexive, you know what a reflex is? It's like a reflection, right? So what we're saying is these are the same. EG and EG, which is what we see here, this diagonal, is congruent to itself. And so that's where we're getting that information from. Then it says, okay, now we're proving that the triangle EFG and the triangle EGH are congruent to each other. So now it's just a matter of, is that, and again, this is coming from previous geometry and knowledge, that is either going to be SAS, ASA, or AAS, one of those. So we can narrow this down because we see throughout our process a few things. First of all, right here, that is a congruent pair of angles. So is this, right? I'll write a 3 there. That is a congruent pair of angles. This is a congruent pair of sides. So I know that my answer has to be either ASA or AAS. Angle, angle, side, or angle, side, angle. It's just a matter of how they are arranged in our diagram. And in our diagram, they are arranged like so. Angle, side, angle. Angle, side, angle. They are arranged angle, side, angle. So that means we are going to choose angle, side, angle. And then we're done with our proof. And so I know some of you may be thinking, I don't know what just happened, but that's okay. I want you to just kind of like listen and kind of take it in because we're going to be doing more of these as we go along. So that's kind of how proofs go. So let's jump down and we're going to jump through all this. I covered a lot of this information in the other video. Questions 2, 3, 4, 5, 6, 7 are all vocabulary words, terms. So you just need to use the notes that I gave along with the text from the lesson to answer those questions. Then we get to another proof. Like I said, I'm going to go through these proofs with you. I'm going to try to move through this one a little bit more quickly. So again, they've given us MNOP. That's MNOP. That's this parallelogram right here. And they want us to prove that MO and NP bisect each other at Q. And we know they bisect each other because we learned that in our notes. If you remember, that was the theorem that we had for right here. Diagonals bisect each other. So we're going to jump back and say that's what we're going to prove. So let's go through the process. So MNOP is given. MN is parallel to OP. So that's coming from the fact that these two lines are parallel to each other. That is just part of the definition of, oh, great. So now I got to go down and look. Definition of parallelogram, G. It's really annoying. So that's going to be the definition of a parallelogram. Okay, so I'm going to write that down here. Definition of parallelogram. That's not a good parallelogram, Mr. Matthews. Terrible parallelogram. All right, here we go. Parallelogram. It's better. Next, angle 1 is congruent to angle 3. Angle 2 is congruent to angle 4. Now, these are 1 and 3, 2 and 4. That should be familiar to you from the one we did up here. When we did that up here, the answer was alternate interior angles theorem. So let's go see if that's one of our options for number 3. There it is. B. Choice B says alternate interior angles theorem. So that's going to be our winner. So let's go there. And that's choice B. Now we see that in the fourth line, MN is congruent to something. MN is congruent to something. And then it says opposite sides of a parallelogram are congruent. They're pretty much giving us the answer. In other words, they want us to find the opposite side. So what is the opposite side to MN? The opposite side to MN is OP. So we should be selecting the answer choice for OP, which is answer choice A. All right, then they're proving a triangle. They're proving that triangle MNQ is congruent to some other triangle. Now, we already know which triangle they're proving because we can see there's a triangle here and a triangle here where we have angles, and we just did this, but we did the side. So we know the other angle the other triangle that's being focused on is triangle OQP or PQO. Let's see what it says down here. There it is, triangle OPQ. Oops. That's answer choice H. We don't need to worry about 6, but we can see they've shown that the other parts of those triangles are congruent. That's what CPCTC means. It means congruent parts of congruent triangles are congruent. And then it says MO and NP bisect each other at Q, and that is going to be the definition of a midpoint, because we see that these are the midpoint of that line. So definition of a midpoint is C. And so you're done with that one. All right, so this video is getting a little long, but that's because there's so many proofs. But we're going to move down here, and I'm going to talk you through these other problems. So you should be able to do number 9 based on the examples that I did in the previous lesson. You're looking at what is congruent to and what is equal to EF. Then you're finding the lengths of EF and DG. EF is here, DG is here. They are equal to each other. So I will tell you right now, the first step in this problem is to just say 4x is equal to x plus 9. And then you need to solve that equation for x. All right. I'm just going to help get you started on all these problems. Similar number 11, you do not need any information except to know what is congruent to DE. You should be able to get that easily based on the examples I gave you. What are the lengths of DE and FG? Again, you should be saying, okay, well, DE is 4y and FG is 3y plus 7. And then you need to solve that for y. What does y equal? All right. You're going to need to solve that equation yourself. Okay, more from the examples that I gave you on the notes. DGF is this angle right here. DGF, that's this angle. What is the measure of DEF? Well, those are opposite. You need to find the property that we learned that tells you about opposite angles. You should be fine on that one. Very similar idea here. DGF. So then therefore, what is DEF plus EFG? Those are consecutive angles. What do consecutive angles add up to in parallelograms? You need to find the property about that. Lastly, DP. DP is equal to what other part? Well, we know the diagonals bisect each other, so you should be able to know what DP is going to be equal to. If this is being cut in half by this, DP has to be equal to some other part. Same thing with this. EP is equal to what? Well, if this is being cut in half, EP, it should be obvious to you what other part is equal to EP. That's very similar to what I did on my examples. And that gets us through lesson 1.